SwayamPrabha. Digital India. Educated India.
Hello all. In this video we will be looking at micromechanics to predict the stiffnesses in a lamina. In the previous video we looked at what we meant by the micromechanics of lamina, and we have looked at some very important concepts such as the representative volume element as well as the few assumptions needed to apply the micromechanics of lamina. So when we say that we are looking at the stiffness prediction, we are essentially trying to predict what are the stiffness properties of a lamina, which include the stiffness along the fibers E1, perpendicular to the fibers E2, the Poisson ratio nu12 and G1. So the idea being, can we predict these if we know the properties of the fiber and the matrix? So we'll start with E1. E1 is the elastic modulus along the fibers. For this, we start with the representative volume element, which we discussed in the previous video. This is the smallest size of the element, which has the same proportions of fiber and matrix as in the lamina. Okay. So to determine EV, we'll start with an assumption. The assumption here is both the fibers and matrix strains are equal in the fiber direction. So here we are looking at the loading happening along the fiber direction. So let's say if this is the RVE and this is the loads applied in the direction 1, sigma 1. Then this matrix, this composite is expected to deform in so and so fashion. So we expect, since we are applying a tensile load, it will increase in the length, but in the transverse direction there will be decrease. But the major point what we are stressing out here is both the fiber and matrix will stretch by the same amount. This is important because let's say if the fiber stretches by some amount and the matrix stretches by an extra amount, then we see at the interface between the fiber and the matrix there is some non-compatibility, meaning the stretch in the fiber and the matrix cannot be different. If they are different, then there is failure. So this is the simplifying assumptions we are talking about. As we mentioned, now we are focusing on the mechanics of materials approach where we do make these assumptions. Okay, once we make this assumption that both the fiber and matrix have the same strain, and we showed you this is the deformed state after applying the loads along the fiber direction. Now let's derive and see how we come with E1. We start by defining the strain in the composite. How do we define strain? It is change in length by original length. So let's say the original length is L, and because of this load we notice a change in length of delta L. Now we can write this strain as delta L by L, as we all know. Now looking at the stress strain relations in the fiber, recall that for the fiber we said we are assuming it to be homogeneous, isotropic and linear elastic. So here we are invoking the linear elastic, saying that the stresses in the fiber is modulus times the strain. But here, instead of writing the strain in the fiber, we can simply write the strain in the composite, because we already made this assumption, and this is not like something unrealistic. This is something what we even expect. Similarly, for the matrix material, again the stresses in the matrix can be written as elastic modulus times the strain in the matrix. But here we have replaced the matrix strain with the composite strain because both are the same. So essentially what we are saying is epsilon 1 is equal to epsilon f is equal to epsilon m. Strain in composite, fiber and matrix all are the same. Okay. So now let's see how is the load distributed. So let's say if we multiply the stress sigma 1 with the cross section area, then we get the load P. So we are saying P is distributed between the fiber and the matrix. How is it distributed? It is, you can simply a product of the stresses in the fiber times the cross section area of the fiber will give the load carried by fibers, and similarly load carried by the matrix is the corresponding stress times the cross section area AM. With this equation we'll do two things. First, we'll divide both sides of the equation by A and multiply both sides of the equation with epsilon 1 on both sides of the equation. So once we divide with A, we get, for the left side of the equation, what we remaining is multiplying with sigma 1 A. So both these cross section areas cancel out each other, and what is remaining is strain times the stress, which is nothing but the modulus E1. And similarly for the right side terms, we got EF, which is the modulus in the fiber, times this fraction AF by A, plus modulus of the matrix times this fraction AM by A. But what is AF by A? This is the volume fraction which we already discussed earlier. So volume fraction actually is defined as the volume VF by V of the composite, volume of the composite. But if we now consider that the depth is constant both for the fiber and the composite, then we can replace this volume fraction with the cross section area fraction. So in this expression now we replace this with Vf and this ratio with Vm. Then we are able to show this relation E1 is EF times the volume fraction of fibers plus elastic modulus of the matrix times the volume fraction of the matrix, which we call it as the rule of mixtures. So this expression is usually called as the rule of mixtures, but in the next slide we'll show how we can plot this variation of the elastic modulus with the volume fractions. So here we are reproducing the same equation we derived in the previous slide. In this plot, the x-axis is the fiber volume fraction Vf. Let's say it is starting from 0 to 1, 0 meaning we have complete matrix, and to the 1 means we have the complete fibers. When we substitute Vf equal to 0 in the equation, we get E1 is Em, and when we substitute Vf equals to 1, we get the E1 is Ef, which means at 0 fiber fraction, the E1 is simply the elastic modulus of the matrix, and when Vf is equal to 1, it is the elastic modulus of the fiber. But we know fibers are much stiffer than the matrix, so the value is somewhere here. And this relation between E1 and the volume fraction is linear, which means it will have a relation something like that. So let's say if you are looking at Vf is equal to 0.5, meaning there are 50% fibers and 50% matrix material, then the value of E1 is midway between the Em and Ef, the fiber stiffness as well as the matrix stiffness. And most often in practical situations we have Vf around 0.6. So this is what we commonly see in practice. The other way of looking at this micromechanics for E1 is we can think of the matrix and the fiber as though these are springs in parallel. So let's say we are applying loads sigma 1 on both sides, and let's say the intermediate one is the fiber and these are the matrix. So previously you remember when we applied this load, we said the whole fiber and the matrix will have the same deformation or the same strain. So this is what happens when we have springs in parallel. But what is the insight we can get from this spring model is, upon loading, which of these takes most of the load? Does the matrix take most of the load, or does the fiber take most of the load? We notice that the fiber takes most of the load. And this is because the fibers are much stiffer compared to the matrix material. But there is another important aspect we need to discuss, which is, in reality, whether the even of a matrix or a composite, is it fiber dominated or matrix dominated? So what do we mean by fiber or matrix dominated? We want to see wherein the fiber will have a greater effect on E1, or will changing the matrix material will have a greater effect on E1. So meaning, let's say for example, we say the E of matrix is 1 and E of fiber is, let's say, 100, right? And then since we said the in practical situations the volume fraction is somewhere at 0.5, what will be the value of E1? We can just plug in this formula. It should give us 0.5 plus 50 is 50.5. Now let's do an thought experiment where we say we double the modulus of the matrix, but we keep the fiber modulus the same. Then let's see what is happening to E1. So 2 times 0.5 will be 0.1, and here it is uh, 0.5 times 150. So essentially what we got is something around 51. But now let's do the other fashion, meaning we don't touch the modulus of the matrix, we retain it at 1, but for the fiber we will double it. So now you can see the E1 will be uh, fraction times 1, so it will be 0.5 plus 200 times half will be 100. So what did we notice? Compared to the initial value, when we double the modulus of the matrix, there was no big change in the modulus of the composite. Whereas when we double the modulus of the fiber, even the composite modulus also changed. So from this example, we can conclude that E1 is a fiber dominated property, because changing the properties of the fiber will have a more significant contribution to the changes in the E1 value. Now let's move to trying to predict what is the variation in E2. E2 is the transverse modulus of the composite. Here too we start with the same representative volume element, but here we make a different assumption. Here we assume that sigma 2 is applied. What is sigma 2? This is the stresses applied perpendicular to the fiber direction. It is assumed to be applied equally for both the fiber and the matrix. And this is also a reasonable assumption, because looking at the way the loading is, the same E2 will be applied both on matrix as well as fiber equally. Here there is no distribution of the load. Instead, we have an equal application of the load for both matrix as well as the fiber. Now let's see how this changes the final relation. So first we start by looking at the definition of strain for the matrix and the fibers. So these are a standard definition of strain, saying that stress by Young's modulus. The only difference is here we replace the stresses in the fiber with the applied stress sigma 2. Similarly for the matrix as well. Now we focus on the height of the lamina, or we can also call it as width of this lamina. So W is the total width, So after application of the load, let's say this changes in so and so fashion. So this is the shape it takes, meaning there is an increase in the dimensions along the loading direction 2, but along the direction 1 there is a decrease in the length. So meaning that this change in the width is delta W. Okay. So delta W can be written as strain times the total width. Since we are looking in the direction 2, we should be looking at strain epsilon 2. So epsilon 2 times the total width will give us delta W, or the change in the width. Now we say that this change in the width is summation of change in the dimensions on the fiber plus change in dimensions of the matrix. So here too we focus first on the actual width of the fibers. So though the total width of the composites is W, what is W times Vf? W times Vf will give you the actual width of the fibers, and W times Vm will give you the actual width of the matrix. So the width times the strain will be the total deflection in the fiber. So this will be deflection of fiber. Similarly, the second term takes care of deflection of matrix, where we are saying V times W will give you the actual width of the matrix material, times the strain will give you the change in the width in the matrix. Okay. Now if I remove the common W in this first equation, now we can write it in terms of the strains and the volume fractions. Okay. Now let's try to bring in the E value. So how do we bring it? We multiply both sides of the equation with E2. So what does E times, or the modulus times the strain, we know is the stress. Similar to the right side of the equation, we are writing again E2 times what is given here. So here we have used this expression for strains in the fiber and the matrix and substituted in this equation here. Now we are able to write in terms of E2. So now once we focus on this equation and consider the first term here and the entire last term here, we notice that sigma 2 is common in every term. So once we remove it, we can write it as 1 equals E2 times Vf by Ef plus Vm by Em. Or in other words, we can write it as 1 by E2 is equal to Vf by Ef plus Vm by Em. This is called the inverse rule of mixtures, which can be again written in terms of E2 as, so the same equation can be written as in terms of E2, and this we call it as the inverse rule of mixtures, because if you look 1 by E2, just 1 by EF and 1 by EM as three expressions, then again it is looking at the rule of mixtures. The only difference is now we are looking at modulus as 1 by E values. Okay, but this time again we'll ask the same questions like what we asked last time, whether it is a matrix dominated or a fiber dominated property. To explain that, let's look at the plot first. So again here we reproduce this expression for E2, which we now said is the inverse rule of mixtures, and usually the plot is somewhat like this, meaning that again we are talking of volume fraction of 0 to volume fraction of fibers to 1. So to the left is the matrix material properties, which are usually small. So here if I plug in Vf equal to 0, we should get simply as Em. and to the right as EF. As we can see, initially even until volume fractions of 50, it is very close to the EM value. Let's say this value is around 0.5. So here too, let's ask the same question, whether it is matrix dominated or fiber dominated. So again, we'll follow with the same kind of example we have done previously, where we said EM is equal to 1, EF is equal to 100, and here E2 should be written as 1 times 100 by, we are looking into the volume fraction of fibers as half, because we said that's where most of the fibers are there. Practical composites have the volume fractions close to half. So for this we said it is half of 1, so 0.5 plus half of 100 is 50. So it is around 100 by 50.5. I would approximate it to close to 2. Okay. Now let's do this example where we say we double the matrix properties and keep the fiber properties the same 100. Then E2 can be written as 2 times 100 by 1 plus 50, where we are now looking at 200 by 51. So it is close to 4, I would say. Now let's look at keeping the fiber properties the same, sorry, matrix properties the same, but we change the fiber properties by doubling it. Now once we try to find this E2 value, it should be 1 times 200 divided by half of 1 is 0.5 plus half of 200 is 100. So it should be 200 by 100.5, which is close to 2. So from this example, what can we conclude? We can conclude that when we change the matrix properties, the variation in the E2 values is high. So because it is doubling, if we double the properties of the matrix, the properties of the composite are doubling. But if we double the properties of the fiber, it is more or less the same. So now I can confidently say that E2 is a matrix dominated. From this example, it is clear doubling the matrix properties double the E2 value, but it didn't happen the same with the fiber. And looking at this example also, we can look at it. But here, let's say the EF value is increasing. So this new curve, let's say with a different color, I can show it takes a trend somewhat similar to this. No, actually it should not be touching the y-axis, but let's say it is going to much higher values. What I mean is, this variation or the delta here happening at 0.5 fractions is very less. But now if the EM value is doubled, now we look at a third curve, let's say with red, then we'll see the curve is somewhat in this fashion. So this is the variation coming from the matrix, and the earlier one is from the fiber, by doubling the properties of the matrix and the fiber. And pictorially also we can see the variations from the matrix are much higher than the variations coming from the fiber. So for these reasons we can say that E2 is a matrix dominated property. And now also let's look at the spring model we are looking for E1. Earlier we said for E1 all the springs were in parallel, but if we are looking at E2, now we should say that these springs are in series, the matrix and the fiber. So let's say this is the matrix value and this is the fiber value, and the applied loads are this sigma 2, So in this we notice that since the matrix is very compliant, when we apply a load, the matrix takes most of the stretches. So that is the reason why it is more matrix dominant. Okay. So we have until now looked at predicting E1 values and E2 values. Now we move into the Poisson ratio nu1. So we know the definition of nu12, meaning that the loading is in the direction 1, and then we are looking at the strain ratio in direction 2 versus strain in the direction 1. And here is the simplifying assumption we are making is both the fiber and the matrix strains are equal in the fiber direction. If you recall, this is exactly the same assumption we made for E1, where we said, let's say this is the RVE, and applying a load sigma 1, we said both the fiber and matrix stretch by the same amount. Okay. So now let's see how we can derive this Poisson ratio nu1. First we look at this delta W, meaning that we say the total width is W. And because you are applying the load in direction 1 and there is a Poisson effect, the transverse dimensions reduce. So we are saying that let's say this is the reduction in the dimension as well as there is a reduction in dimension here. Both of it is captured through delta W. Delta W is the decrease in the width because of applied load sigma 1. How can we write the change in the width? We write it with total width times the strain in direction 2. So we already showed that epsilon 2 can be written as Poisson ratio nu1 2 times the strain in the direction 1. Similarly, I can apply the same expressions for the matrix as well as the fiber, where we showed the change in the dimensions in width is given in terms of the total weight, volume fraction, Poisson ratio of the matrix, and the strain. Similarly, here the total weight, volume fraction of fibers, the Poisson ratio of the fibers, and the strain in the fibers. Now let's see how we can club these expressions. So we start with saying that the total change in width is because of change in width in the matrix plus change in width of the fiber. To write it as for delta W, I can replace it as W times the Poisson ratio nu1 2 times epsilon 1 equals. For the matrix, it is W, the volume fraction V M, the Poisson ratio M epsilon 1 plus W. So in this expression, we see epsilon 1 is there in all terms, so we can get rid of this strain. Similarly, the width is also there in all terms, so we can get rid of that. After that, we can simplify this expression and write it as the Poisson ratio is given in terms of Poisson ratio of the constituents and the volume fraction of the constituents. Again, we see the expression is the rule of mixtures, what we have been seeing for E1 as well. And here, can we comment on whether it is matrix dominated or fiber dominated? For that, we have to look at what are the values of the Poisson ratio for the matrix and the fiber. Are they very different? The answer is no. Usually the Poisson ratio are very close because these are in the ranges of 0 to 0.5, but most often very close to 0.3. Since these values of Poisson ratio of the matrix and Poisson ratio of the fiber are close, now we should say that it is neither matrix dominated nor fiber dominated, because this is very different from E1 and E2. In E1 and E2, we said one of it is fiber dominated, the other is the matrix dominated. Whereas when we come to the Poisson ratio, since there is no big changes in these individual constant properties, we said it is neutral. So since it is this, we call it as neutral. Okay. Lastly, now let's talk about the shear modulus. Here we again start with the same RVE, but now let's see if we apply a shear load, how the deformation is. So we notice that these fibers are stiff, so the change in the shape is small. But the matrix materials are less compliant, meaning the change in the shape is large. Okay. So what is the assumptions we are making here? We say both have the same shear, both on the matrix and fiber. So you apply the same shear stress. Let's say we are talking about tau 1 2. The same shear stress will be applied for the matrix as well as the fiber. Here we are not distributing the shear stress, but the entire shear stress is applied on each of these constituents. Now let's look at the deformation. So let's say the total width is given by W, and of course W times VF will give you the width in the fibers, and W times VM will give you the width in the matrix material. But delta here is the, because of the change in the shape, there is, let's say if we consider about this is the delta we are looking at. So delta is the total movement what we see here, which is a contribution from matrix as well as the fibers. So how do we write this delta? We write it as shear strain times the total width W. W we have already shown, and shear strain is what we'll be looking at from now on. So we can use the same expression for matrix and fibers, because we already said the product of W times VM will give you the actual width of the matrix, and W times VF will give you the actual width of the fiber. That times the shear strain will give you the change delta M and delta F. So we can start by saying this delta is split into delta M and delta F, which means the changes in the deflection from the matrix, if you add it with the changes of the fiber, will give you the total change delta. Or in other words, let's say this is the change we see in the fiber, and here this is the half of the matrix, because we also have the other half at the bottom. So this is delta M by 2, because there is another delta M here, which is the other delta M by 2. So basically we are saying this delta is partially from the matrix and partially from the fiber. Now we write it in terms of the shear strain gamma. How did we write? We multiplied both sides with W, and then W is taken in the denominator. So shear strain, total shear strain is simply written in terms of the individual shear strains times the volume fractions. But now let's see the volume fraction. We know that the shear strain is given as the ratio of the shear stress to the shear modulus. Similarly, we can write expressions for the shear strain in the matrix and shear strain in the fiber. And once we plug in these equations in this expression, we get the shear stress tau by G12 written in terms of the same ratio times the volume fractions. And since we have the same shear stress applied in the composite and the constituents, we can now write it as 1 by G12 is equal to volume fraction of the matrix by shear modulus of matrix plus volume fraction of the fiber by shear modulus of the fiber. This, as we discussed earlier, is the inverse rule of mixtures. Of course, this can again be rewritten for G12, and which is shown here. G12 here is again written in terms of the shear modulus of the constituents and the volume fractions. But again, now come back to the same question to see whether this G12 is a matrix dominated or a fiber dominated. So we have already seen that for an inverse rule of mixtures, this is similar to E2. E2 also we got where it is inverse rule of mixture. There we concluded that with the inverse rule of mixture, it is matrix dominated. So here too we can say that shear modulus is matrix dominated simply because it is a inverse rule of mixtures, and we know that the properties of the matrix are much lower compared to the properties of the fibers. In summary, what we have seen in this video is we looked at predicting E1, E2, Poisson ratio and the shear modulus. First, for E1 we said it followed the rule of mixture. But for E2 and G12 it followed the inverse rule of mixture. And for the Poisson ratio it followed the rule of mixture similar to E1. And talking about whether it is fiber dominated or matrix dominated, we said E1 is following the rule of mixtures and it is fiber dominated, but whereas E2 and G12, which is the transverse modulus and the shear modulus, both of them are matrix dominated, and without coincidence we can see that it is again rule of mixtures. And finally, for this new one too, we said it is neutral. The reason why it is neutral is because the properties of the fiber and matrix, especially for the Poisson ratio, they are almost close to each other. There is no big differences. But whereas the modulus of the fiber and matrix are very different, similarly the shear modulus is also very different. So this should summarize the expressions we derived for predicting the properties of the composite based on the constituent properties as well as the volume fractions Vf and Vm. Okay, thank you.